Hey, this is Mr. Vandegrift, and this is Populations and Resources. Too Many Jellies, Chapter 2 review. Again, I'm just going quickly so you can pause anytime if you want to read the text. I just want to do a quick video review of Chapter 2. And so we talked about reproduction and energy in 2.1. There's learning intention, success criteria. And then again, how you log in to Amplify is you use Clever. And then you go from there to the population's resources. Then you click on the turtle. And now we're in Chapter 2. So Chapter 2, you've got all our lessons here. And the first one, we did a warm-up. What idea do you have about what causes the number of births to increase in a population? We had some class discussion. We did some models on the claims. Talked about reproduction. Then you had some different articles to read. You could either read the one on the salmon or the penguins or the fireflies or the elephant seals. You annotated that. You found a partner. You had some discussion. Talked about energy, the ability to make things move or change. Then you did some homework. And then we zoomed in. We took a little time with the simulation again to kind of play around with that and get used to some of the features. And then we opened up with this question is what do organisms need in order to reproduce, and citing evidence from the articles. Then we went into lesson 2.2, learning intention, success criteria. And we came up with, well, in order to reproduce, organisms need to eat. This is because the food contains energy storage molecules, which are molecules that can release energy in the organism's body. And we talked about energy storage molecule is what organisms need to survive to release energy. Organisms need to release energy in the form of energy storage molecules in order to reproduce and also do a lot of other things. Spend a little more time with the simulation. And then from there, we talked a little bit about, hey, everything you eat is you're eating it as a fuel because there's energy in there, whether it's a starch or whether it's glucose or whether it's a fat or a lipid. I think we lit some of your potato chips or your lunch on fire. I think it was the Cheetos or the Takis that seemed to have the biggest flame, releasing the most energy. There's a lot of oil, a lot of fat, and a lot of carbohydrates in there. And so through a chemical reaction called combustion, there's a lot of energy given off. That takes place on a much smaller scale through cellular respiration in your cells and in the organelles of mitochondria. And then we talked about a key idea that organisms in consumer populations get energy storage molecules from, of course, eating organisms in the resource population. Then you were able to design your own yeast experiment, the single cell fungus. They love to eat sugar, and they reproduce very quickly. So in cup 1, you put no sugar. Cup A, you put no sugar. In cup B, you put 1 pinch, and then in cup C, you put 1 teaspoon of sugar. You made a prediction, developed a hypothesis, conducted your investigation, set it aside. Then we reread the article to pull more information out. After that, just wanted to highlight again a couple students' exemplary annotations. I was really, really proud of how well you're interacting with the text, how you're actively reading, and then from that having really good discussions. There's Lily, her details here. We got John, his details here. We've got DeShelly. Just wanted to highlight some students there, so congratulations. You made the highlights. And from there, the key concept was the more energy storage molecules available to a population, the more the organisms in that population can reproduce. That's a cross-cutting concept of energy and matter. We want to track the energy flow. From your article, you did that. We returned to our experiment, and lo and behold, we realized that more energy storage molecules available to a population, the more the organism in the population can reproduce. Then we had to put things on pause because the COVID-19 virus pandemic wasn't really hitting the United States yet, but it was slowly sweeping across the world. So we took some time to go here on this website And you can see here, right then when we were looking, there was only 4,000 deaths. I think Italy right now at least has 10,000. It only had 463 there. And there's quite a few more cases. I think there's at least that many cases in the United States. This was worldwide. I wish I had a date on this. This is probably 3 weeks ago. And then I asked what questions you had about the pandemic. Then we talked about literally how small viruses are. So if you look at the grain of rice and the coffee bean, grain of salt, there's an amoeba, then there's a paramecium, there's a human sex cell egg, there's a sperm, and then you just keep going. There's a red blood cell, Baker's yeast, and then there's even a bacteria. We still don't see the viruses yet, but then we get down to HIV virus, influenza virus. So we're looking at these viruses, probably back up here, hepatitis virus. So the COVID-19 coronavirus in here is probably around this size, I would venture to say, in here. So let's zoom back out. You can see the importance of washing your hands and how small these things are. It's just unbelievable when we look at it. And that would take us to the cross-cutting concept of scale and proportion when it comes to the cross-cutting concepts. And we talked about viruses and how they can even infect bacteria, and then they just kind of take that cell hostage, whether it's one of our cells or bacteria, and then take its machinery, and the cell's machinery makes more of the virus, and that's what it even does in our own body. So the virus is very smug about it, like, hey, look what I did, because that's their job, and our immune system's job is to dismantle or kill that virus, right? So there's different methods. We already talked about this. There's two methods that viruses will reproduce. One is lytic, and the other is lysogenic. So we briefly talked about that.
So let's say that this guy has the flu, could be any flu, and here's a droplet from his sneeze containing, if you move in and kick a really close.
And you can see this little mucus, it's just floating in the air, has thousands of viruses. So again, that's why the social distancing is so important. Talked about the anatomy of the sneeze. Then we talked a lot about cells versus viruses. And then we talked about bacteria. We talked about vaccinations. So we kind of just took a pause on our lesson for, I think, half of the period. And then we returned back to the yeast experiment. Remember that there's our sugar, there's our yeast, and then we put the warm water to activate the yeast. Then we came up with our questions, and then we watched what took place. So if you look at the time lapse here, this took place over probably 10 to 15 minutes. And again, cup A has no sugar, cup B has a pinch of sugar, cup C I think has a teaspoon of sugar. But a really interesting question is, if you look at this video, you back it up. Even cup A reproduces or grows a little right here, but there's no sugar in there. So see if you can answer that question. Why would cup A rise even though there's no sugar in there? Then I asked you to draw a model. You guys came up with some amazing models. I wasn't able to update that yet. Talked about what's going on with the bubbles, that the yeast cellular respiration, and one of the byproducts is going to be CO2, carbon dioxide, which we're even breathing out with our cellular respiration. And that's what's causing the bubbles. It's causing bread to rise. You can see those bubbles rising there. And then the key concept here would be the more energy storage molecules available to a population, the more the organisms in that population can reproduce, proving that the one that had the more sugar, the bubbles were higher, there's more CO2, and we infer that there was more reproduction taking place. And then you saw the video of the crickets and the reproduction there, and I think we kind of compared and contrasted this with the Venn diagram. You guys did a great job with that. And then you can see here that when it only had a little sugar to feed on the crickets, there was only 10 eggs, more sugar, then they produced 50 eggs. So again, very similar here. You should be able to explain this, why there's more bubbles in cup C, why there's more eggs in group B from the crickets. Excuse me. And we talked a little bit again about cellular respiration taking place in our lung. We breathe in oxygen, and we eat like a Julian apple pie, glucose, and then with that, we through in our cells with the mitochondria, we kind of cell breathing, we call it cellular respiration, where we create energy, and then we breathe out a waste product, which is CO2 and water vapor. The more energy storage molecules available to the population, the more organisms in that population can reproduce. So I think we got that. Then we did lesson 2.3 and started talking about food chains and food webs. Key concept is the larger the resource population, the more energy storage molecules are available for the consumer population. And we went back to our sim, and we were at page 40 and 43 if you want to look over that and review. I think by this time most of you are really good at using the sim modeling tool, changing the number of bursts. So how'd you do that? Make sure, again, you can hit this analyze, see what's going on here, and then over here you can lock different parts of the ecosystem and then kind of engineer what's going to happen. And you want to look for patterns and relationships as well. And then we talked about the mouse plague of Australia. So you might want to show some people at home that, maybe your siblings or your parents, kind of that explosion that took place with the mice in Australia. What do they call it? The Australian mouse plague? Mice plague? Mouse plague, yes, there we go. Mouse plague horror in Australia is the name of the video there. And again, that happened from an abiotic factor where there was so much rain. One of the seasons, a monsoon brought in a lot of rain, a lot of crops, a lot of plant growth, more food for the mice to reproduce, and it just got out of control. The larger the resource population, the more energy storage molecules available for the consumer population. Then I gave you some homework on page 44 and 45. We went to lesson 2.4, the deaths changing in a population. Just kind of review that on page 47. And then what can change the number of deaths in a population, that was on page 48. The larger the consumer population, the more energy storage molecules it will need. Therefore, it will eat more, causing more deaths in the resource population. And let's see here. Homework, that was a 51, 52 you're supposed to complete. And then now we are at lesson 2.5, which is the critical juncture, or if you're a Mrs. Reynolds or a Mr. Cranock's class, you've already done that. So my class needs to take this, and then we're going to kind of move on, finish chapter 2, and go to chapter 3. So I'm excited to be on this journey with you, and thank you for listening to me speed talk through this. Again, pause it at any place. It's just a review. So hopefully this video was helpful.